Hi, welcome back. We are continuing with RISC-V assembly, so let's see those instructions that do data transfers to and from the memory. Remember the picture from early in the course when we introduced the principle of memory hierarchy. The processor core was at the very top with its registers. Registers are extremely fast. They share that precious real estate with the processor core and therefore are extremely expensive. So we have a small number of them, to be precise, 32 total. Now, on a separate chip, typically there is the main memory. It is implemented in a different technology. It is called DRAM, which stands for Dynamic Random Access Memory, and it comes in different flavors. You might have heard of double data rate, which is DDR, and it comes in different generations, 3, 4, 5, or maybe high bandwidth memory, which is HBM, and that also has different generations too. There is HBM, HBM2, and then now we are getting to HBM3 generation. DRAM is also fast, but not nearly as fast as the registers. It is priced reasonably. You get a lot of gigabytes for a few tens of dollars, and has medium capacity compared to mass storage that we have in disks and solid-state drives. But the question here is, how big is this gap in the pyramid? How much a register is really faster than a memory? So given that there are 32 registers, 32 bits each, total of 1024 bits, meaning 128 bytes total there. On the other hand, in DRAM, we may have in a low-end laptop about 2 gigabytes, in a high-end laptop up to 64 gigabytes of memory, and a server may have a terabyte of memory. And the physics dictates that smaller is faster. Main claim to fame of Bruce Lee, for example, or typically point guards are a lot faster than centers in basketball. How much faster are the registers than DRAM, really? So when we put that on a piece of paper, we will find out that the numbers work out that they're about 50 to 500 times faster. So that's in terms of latency of one access, or the first access to DRAM, to get one individual data item. That access takes a few tens of nanoseconds, and you compare that with a fraction of a nanosecond that it takes us to access registers. Keep in mind that this is for one isolated access. Many subsequent accesses to nearby memory locations will go faster. To put this in perspective, a great picture to keep in mind is this picture of Jim Gray's storage latency analogy. What we have on the left-hand side are our registers, and they take about a nanosecond to access. Memory takes about 2 orders of magnitude more, so 100 nanoseconds. Let's try to make an equivalent to tasks that we do as humans. So for example, if we would like to retrieve data from our heads, let's say that the retrieving data from a register that is in our head would take about a minute. So what is that takes 100 times longer? Where would that data be? Well, when we are all in Berkeley and live and all that, it would be normal to make an analogy to driving to a town. For example, we forgot a piece of paper somewhere and we are going to go and retrieve it. Let's say that town is Sacramento, which is roughly 100 minutes away, or hour and a half away. That's big penalty on time. We can do a lot of stuff in an hour and a half. Or if that gap is 500x, that it may be the case in some cases, in 500 minutes we can make it to Los Angeles and back. It would not be convenient to leave that piece of paper with our data in LA and have to go to retrieve it, or Sacramento. So this is there to try to illustrate how expensive is it to have to go get the data from the memory. Let's try to see how do these instructions look like on a simple example. So the first one that we're going to look at involves loading from memory to register. So this is a simple code that that's in C, and we'll try to translate it into RISC-V assembly. So let's go by line. So what we have here, we have a declaration of an integer array of 100 elements, and then the second line very simply takes element A3 of that array and adds it to the variable h and stores the result in a variable g. I'm using kind of assembly terminology again, but you guys know what I mean here. So we know how to add things in registers, so we need to figure out a way how to get the value of this third element in the array that resides in memory to our register. We need a new instruction there. So that new instruction is showing up right here. It is load word. So load word in RISC-V goes to the memory and loads from the memory to a register. So the syntax is fairly straightforward to understand here. Take a look. This is my destination register. So mnemonic is LW, destination register, and then we have this. What does that mean? We have to specify the base register, which is the pointer to the element A0 of the array, and then specify the offset to the element of the array that we would like to retrieve. So the base pointer points with an offset of 0 to the element A0. We would like to get the third element in the array. But remember, we are storing integers in this array. They're 32 bits wide. 32 bits is 4 bytes. And RISC-V addresses each byte in memory. So we need to specify this offset in bytes. 3 words is equal to 12 bytes. So that's why this offset is specified as 12. That's why we have 12 here. So the actual address of the datum in the memory is calculated as the address of the base pointer, which is the content of a register x15 plus 12. Very well. So keep in mind that this offset must be a constant known at the assembly time. So if you picture it, another thing to remember this syntax well is the direction of the data flow within the instruction that kind of mimics what we see in reality. So data flow goes from right to left, like what we have seen in other instructions. So add instruction also moves the data from right to left. We add contents of registers x12 and x10 and store the result in x11. So that kind of should resemble a picture that we have had in the previous segment. We take data from the right in the memory and move it to the left to the registers. So we load from memory to registers. We are going from right to left. So to recap what we have seen here, we have essentially translated this C code. One note to make here, there is no really assembly instruction for now for the translates, the declaration of allocating this integer array. All what we are translating is this one C instruction that adds h plus a3 and saves it as g. So what we have there, we first load the contents of this memory location, specified by the base pointer plus the offset to a temporary register x10, and then we add the contents of x10 with x12 and store the result in x11. Notice that we could have been a little bit more optimized here and could have saved this, could have reused register x10 for the variable g. Okay, hopefully this made sense. Let's see the other instruction. The other instruction that we need is to store from the register to the memory. So it goes the other way. We have something in the register and we want to put it in the memory. And here is the example code, exact same code, except that we have changed a bit in it. Instead of saving it in a variable G, we will need to save it in another element in the array, which in this case is A10. It is offset by 10 words from the base pointer. So the first two lines are identical as what we have had before. We did get a little bit better here. We have learned we are reusing extend as a temporary variable, and now here comes a new instruction. This new instruction is store word in RISC-V. That store word in RISC-V does the following. It takes the contents of a register x10, where we have saved our temporary result, and moves it to a memory location that is addressed by the base pointer and the offset. And in this case, since we want to write in the 10th element of the array, we have to specify the offset as 10 times 4 bytes away. So that is 40 is the offset here. So that's why we have 40 there. The data movement or data flow here is the other way round. We are storing from the register in our picture to the memory. And the data flow is going from left to right. Okay, very well. So that should hopefully keep confusion out of the way. We are always in this syntax. The load operations are moving data from right to left. In store operations are storing from register to memory, and it is moving from left to right. One thing to keep in mind, these offsets for loading and storing should be multiples of 4. It's written here as must, because that's a really good practice. One slight disclaimer, RISC-V ISA allows for misaligned memory accesses, meaning that it allows you to scribble, to start writing in the middle of one word and then write a half of a word in one memory location, then another half in another memory location. But that's not advisable. It is just there to support some legacy code. We should not do that, because that would be something that is very, very slow, and it's really messy. We don't want to be just scribbling all over the memory. So you should take this should really as a must. Now keep in mind that these load word and stored word instructions support essentially taking the entire 32 bits from a memory location, a word from memory, and putting it into a register. So they fit really nicely. It's 32 bits to 32 bits, or when we are storing to the memory, we take 32 bits from a register and place it into a memory. But often we operate with different kinds of data types that are not necessarily 32 bits wide, so it would be wasteful to use 32-bit memory locations to store just 8 bits worth of data. Like when we are storing characters, when we are storing, color channels that are typically all 8 bits wide. So RISC-V is conscious of that and supports shorter operands. So it allows for load byte and store byte. The format is exactly the same as what we have seen in load word, store word. As we see here, so we have load byte. It loads a content of a memory location specified by the base pointer x11 with an offset of 3 bytes to a register x10. So it is the same as what we have seen before, with one difference, is that this offset now really doesn't have to be, and shouldn't be 4, because we should be able to pluck any byte from any part of a word and write it in our destination register. Now, by convention, when we take that byte, no matter where it is stored in the memory, because all characters can be packed right next to each other as bytes in a word, so we would be indexing those memory locations by 1, it will copy it to the low byte position of the register extent. So if this is our register extent here, no matter where it picks the byte, and in this case the offset is 3, so it'll take the highest byte, the most significant byte from that memory location that X11 points to, it would write it into low byte position of register extent. There is another important thing to keep in mind here. We don't know what kind of data types we are operating, but in many cases we will be operating with signed numbers. So remember, in signed numbers, if it is a 2's complement number, this first bit of a byte determines what is the sign, whether that number is positive or negative. By looking at it, if it is a 0, the number is positive. If it is a 1, the number is negative. So what should we do when we copy this byte to our register to preserve its sign? So if we just write zeros in the upper 3 bytes, well, then no matter what the number was, we are going to make it look like it's a positive number. We do have to preserve the sign. So the way how we preserve the sign, we take a note of that top bit, the most significant bit in a byte, and copy it over. That copy over is called a sign extension. And the way how it looks in this picture, we actually take that bit and smear it all over the upper bytes in the word. So we take the most significant bit out of that low byte and smear it over like avocado on a toast. Make sense? So that's sign extension. We don't always want to do sign extension. So if we don't want, if we are certain this is not a signed number that we are transferring from memory, it is a character or something that is always a positive number, like color intensity. RISC-V supports load byte unsigned, which is another instruction that copies a byte from a memory, loads a byte from memory to a register, but does not do sign extension. So it just fills the upper bytes with zeros. A question for you: why there is no equivalent of that, no unsigned store byte, so no SBU? Well, it doesn't make sense. We're just taking a byte and plugging it into a memory location. There is no sign extension that is happening. We don't have to fill out anything there. Now, LBU has exactly the same syntax as LB. All right. So let's do a little of an exercise here to see how all this clicks together. So the question here in this example is, what is in X12 after these 3 instructions are executed? And feel free to pause here, work it out yourself, or you can just follow me as I do it. So these are the 3 instructions that are fairly straightforward. The first one essentially stores 3F5 in register X11. The second one stores a word, stores the content of X11 into a memory location that is pointed to by the base pointer X5 with no offset. So it just takes that address that is stored in X5 and writes right there. And then finally, the last instruction, LB, takes byte with offset of 1 from that same word and writes it in X12. I think you got the picture. If you haven't, let me walk you through that. So what we have in X11 after the first instruction is this. We have F5030000. Let's say that X5 points to this location. So then this content of a register X11 will be written exactly there. So we are going to get F5030000. Now when we say load byte with an offset of 1, which byte are we going to pick? So this is a word with an offset of 0. The next word in memory has offset of 4 because we are byte addressing the memory. So the byte that has an offset of 1 is this one. So load byte is going to take the contents of this byte of that word, second byte in that word, or the second to the least significant byte in the word, and write it here. So it'll be 03. We'll take a look at the most significant bit in that word and sign extend it to fill the rest of the register with zeros. Hopefully this is a good illustration and you get to practice a few of these afterwards. One little final note. We have only introduced about 8 RISC-V assembly instructions, and one who is paying good enough attention here might notice that at least one of them is redundant. It's add immediate. We really don't need add immediate. We can replace add immediate with a sequence of 2 instructions that we have here. We can store a constant in the memory, load it from the memory into a register, and then add that new immediate to a content of another register, and voila, that is add immediate. So what's up with that? Why do we have redundancy in RISC-V? Isn't reduced instruction set computer supposed to be really lean and mean? Yeah, this does not change the fact that this is a reduced instruction set computer. Add immediate is necessary because these 2 instructions, if we didn't have add immediate, those 2 instructions would be very slow. We would have to go for every immediate to Sacramento to get it and then do the addition. That would be a really, really low performance machine because add immediates are very frequent in assembly code. So this is here, the instruction there is necessary to support the common case, and a common case is adding immediates. There is one big difference between these 2 instructions. We'll touch on that in just a little bit in a couple of segments, but the point here is immediates in the instruction field are limited. They have to be less than 32 bits because we have to store other information. So immediates are a short part of the instruction field. So the range of immediates in ADDI is relatively short. If you need a longer immediate, we would have to load it from a memory, or there may be other mechanisms to generate it. But we'll pause here. I'll see you in a bit with more RISC-V instructions.